As we have already discussed, QAM is a method of combining two amplitude modulated signals into a single channel in order to increase the effective bandwidth of the system. In a QAM signal, there are two carriers which are 90 degrees apart. One signal is called the I signal or in-phase signal, and the other signal is called the quadrature signal or Q signal. Mathematically, these signals can be represented by a sine wave and a cosine wave. These two modulated carriers are combined together at the source for transmission, and at the destination these two carriers are separated and the data from each channel is extracted to reproduce the message signal. A QAM system can be used to transmit two analog signals or two digital bit streams. If we are transmitting analog messages, we have to use amplitude modulation. If we are transmitting digital bit streams, we will have to use amplitude shift keying in the transmission part. The two carriers that we use are at 90-degree phase, which is a condition known as orthogonality or quadrature, and due to this condition, the data can be extracted at the receiving end using coherent detectors. And as we know, in the modulation of two carriers, there will be change in amplitude and phase of the resultant signal. So we can say that this is a mixture of amplitude and phase modulation. Now let's take a look at the modulator and demodulators used for QAM transmission and reception. We already saw the structure of IQ modulator and demodulator. This QAM modulator and demodulator is having the same setup. First, we have to have a local oscillator which produces a constant frequency and a constant amplitude signal, which is usually a cosine signal having an amplitude of A and frequency omega c. And then to generate the 90-degree shifted version, we will use a 90-degree phase shift network which will produce a sinusoidal signal, but both will be having the same amplitude A and same frequency omega c. Two product modulators have to be used to modulate the two input signals that are to be given as input to the modulator. These two inputs can be two analog signals or two digital signals. Two messages can be transmitted simultaneously. These two inputs will be modulated onto this one message signal will be modulated to this cosine signal, and one input will be modulated to the sinusoidal signal using product modulator, and their outputs are combined or summed together and the QAM output is generated. This output is transmitted to the long distance, and at the demodulator end we will need to have the same setup of local oscillator and 90-degree phase shift network and product modulator, because as we know, this is a coherent system. A coherent system will need the same local oscillator which generates the same frequency and phase signal at the receiving end. So if we have such a setup in the receiver or in the demodulator, we can give the received QAM input into the product modulators, where the received signal will be again multiplied with the same carriers. That is, the received signal will be having a combination of the sine wave and the cosine wave. That combined or multiplexed signal will be multiplied with a cosine signal and a sine signal, and those outputs will be containing high frequency components of sine and cosine waves, which are to be filtered using two low pass filters, and the output will be the amplitudes of the two channels. That is, at the output of this low pass filter, we can filter out the high frequency components which are generated by the multiplication of these sine waves to the multiplexed signals, and the output will be the amplitude of the path, or output will be the message signals. This will be the message signal 2, that is the input 2, and here we will get the output 1 or message signal 1. Now we shall see how the whole process is mathematically modeled. This is how the multiplexed signal is mathematically expressed. Here it is considered that the in-phase component is sinusoidal signal. That's why this I of t message signal is multiplied with the sinusoidal signal, and the Q of t message signal is multiplied with the cosine signal. But as we discussed, conventionally we will consider the cosine signal as the in-phase component. So this will be the commonly used equation. This will be the equation that we will use. That is, the here this I of t is the message signal in the top path, and the Q of t is the message signal in the bottom path. So this I of t message signal is multiplied with the in-phase component, and the Q of t message signal is multiplied with the quadrature component. So the sum of them will be the output QAM signal, which is a multiplexed signal, which is a combination of the cosine and sine signals. So this is the transmitted signal. Now in the receiver, the transmitted signal, this signal is received at the receiver, and this multiplexed, or this combination of this signal is again multiplied with a cosine and a sine signal that is generated at the receiving end. So this SC of t, this whole signal is multiplied with a cosine signal in the upper path. So here you can see this component and this component is multiplied with cos 2 pi fct. Both are having same frequency, same cosine signal. So both the components are multiplied with the cosine signal. So after multiplication we will get the amplitude of the message signal and then two high frequency signals. These two high frequency signals are filtered out using our low pass filter, and in effect we will get the message signal alone at the output of the low pass filter. Here in this process we have multiplied with the cosine signal only, that is why we recovered the I message signal only. If we need to recover the Q message signal from this combination of signals, we have to multiply this combination with a sinusoidal signal. So instead of this cosinusoidal, we have to multiply with a sinusoidal signal, and we will get the Q of t as output here. So by multiplying with the sinusoidal and cosinusoidal signals in the upper and lower paths, we can extract the input message signals in the output. We have already discussed the advantage of QAM, that is the increase in the bandwidth of the system. That is, if we are using a amplitude modulation system, it will be taking double sidebands and will be possessing a certain amount of bandwidth. If we are using QAM in the same bandwidth, we can multiplex two signals by using the property of orthogonality. So we can double the bandwidth of the system. That is the advantage of QAM. Now coming to the applications of QAM, both in analog and digital formats, QAM is used. In the analog systems, QAM is used in PAL and NTSC television systems to carry different channels and color and black and white informations. And it is also used in stereo radio systems where two channels are transmitted through two different paths or two different I and Q channels. In digital formats, QAM is used in a lot of applications where the most mentionable uses are in LTE wireless systems, WiMAX, Wi-Fi. Everywhere QAM is used.